In the previous unit, we talked about radial acceleration. Radial acceleration leads to a change in direction of the velocity. Now we're going to talk about the forces that lead to that radial acceleration. So remember, force causes acceleration, which causes the change in velocity. Now, radial force is not a new type of force like force due to tension or force normal force of gravity is. Instead, it's a new direction of force, where in the previous portion of this chapter, we did force net in the x and we did force net in the y. Now we're going to have force net in the radial direction. Remember, the radial direction points towards or directly away from the rotation point. Now we need to discuss how we identify which forces, like the force due to tension, the force of friction, how do we know when they're acting in the radial direction, so that you can sum those forces in the radial direction, just like you did with force net x and force net y. So I'm going to start with the same scenario that I used when I talked about radial acceleration, and I'm going to talk about having a star and a planet. Now, according to Newton's first law, an object in motion stays in motion unless an outside non-zero net force acts on it. So as the planet has its orbital velocity, it wants to continue like this, but it doesn't. Instead, it follows a path around in a circle. So we need to ask ourselves what force is holding the planet in its orbit, and that is the gravitational force from the star on the planet. So the star is exerting a gravitational force in this direction. So as the planet orbits, since the star is at the center, that force always pulls it inward. So as the planet's trying to go off in this direction, there's a force that tugs on it and pulls it inward. And it's always pulling it inward as it's trying to go tangent to the path. So as it tries to go this way, it's tugged here. Here it's trying to go off this way, but it gets tugged that way. So that's what pulls it into that circular path, is that gravitational force acting in the radial direction. Another example I can give you is going around a curve in a vehicle, something we often do around here in the Baltimore area because we're always entering or exiting highways. So here it's not typically a full circle. Instead, you're looking at a curve where you can sort of imagine where the center of that circle would be if it actually was a full circle. Now here, really you got to place yourself in that vehicle. As you go around the curve, the vehicle actually follows the curved path. But if you imagine yourself in that vehicle, what happens? So as you're at this spot, your body actually gets pulled outward a little bit. So that's why you always get, as you go around that curve, and you can usually feel this if you go a little faster than you're supposed to. I don't encourage you to try this. And you get pulled to one side of the vehicle or the other, because the tires are in contact with the road. So the tires are experiencing that radial force, but you are not. So you're obeying Newton's first law, where your body wants to go in that path that is tangent to that circle. And until you hit the side of the car or your seatbelt, there's no outside force to stop you. But the tires are experiencing frictional force, which actually acts inward to hold the vehicle in that circular path. So it's actually a force due to friction that is causing the vehicle to not slide out of the curve. So it's, oddly enough, it's actually a static friction because you're not sliding out of the curve. So this is why you tend to see barriers on the outside of exit or entrance ramps or large curves, because you tend to slide out of them rather than sliding into them. The same reason when you go around the curve, you always go towards the outside of the curve rather than inside a curve with your body, because there's a point where you can go too fast, and therefore you overcome the frictional force and you slide out of that curve. So that's why there's suggested speed limits. Remember, when we calculate radial acceleration, it's v squared over r, so that velocity does matter. So in cases like this, as I've been saying, it's the frictional force that acts in the radial direction that keeps the tires from sliding out of the curve. Otherwise, your tires would experience the same effect from Newton's first law of moving without any change, because there would be no outside force. So you're only getting that change in motion or change in direction when you're experiencing that frictional force, which leads to a net radial force. Now, before I get to a slightly more complicated scenario, I do want to go back and talk about how you would actually write Newton's second law for this concept. So what we're doing here is we're summing forces in the radial direction. So we're starting with the idea that force net in the radial direction equals mass times acceleration in the radial direction. Just like we had force net in the x equals mass times acceleration in the x. And force net in the y equals mass times acceleration in the y. So in our first scenario, the forces acting in the radial direction was a force due to gravity from the sun on the planet. So we would replace force net in the radial direction with force due to gravity and leave mass times acceleration in the radial direction. And remember, acceleration in the radial direction is v squared over r. Over here, we still start from the same spot. We're summing forces in the radial direction, but the only force acting in the radial direction in this case is the force due to friction. So we replace the force net in the radial direction with the force due to friction, and then we have mass times acceleration in the radial direction. Alright, so I want to introduce you to a slightly more complicated scenario here called banked curves. So you have to imagine here something like a NASCAR racetrack where you have a circular path, but the circular path the whole way around is at an angle. So it's really hard for me to draw. I'm going to end up drawing something that looks like an inclined plane on the page here, but I would encourage you to locate a video or something of a NASCAR race if you've never seen one before, to see what I'm talking about in the racetrack. Another place you might see this is toboggan racing, like during the Olympics, where you have, when they go around curves, you can actually see the toboggans actually go up on the curve of the racetrack in order to, we're going to find out, that's the only way they don't actually end up sliding out of the track. So let's talk about banked curves. So as I said, this is going to end up looking like an inclined plane, but remember we're looking at sort of a slice where the track is going to go into the page. So the vehicle that's actually we're discussing here, this is actually the tail lights of the vehicle, so the vehicle's going into the page. Now, banked curves are a way of allowing a vehicle of whatever sort you want to use, whether it's a race car or a toboggan, go around a curve without sliding out of the curve without friction. Because something like tobogganing is done on ice. Race cars, if you actually look at the tires, they're incredibly bald. That's why they have to change them so many times during the race. In fact, if a race car driver actually stopped, their vehicle would actually kind of slide down the racetrack, because they minimize friction as much as possible and still to have the wheels turn. So whenever we do banked curves, we're going to assume that they are frictionless. Doing banked curves with friction in them adds a whole nother layer of complexity into breaking forces into components, because the friction would have a radial component and an x component, and that's incredibly messy. So whenever we're dealing with banked curves, we assume we're dealing with a situation where the friction is minimal and can be ignored. Alright, so if we don't have friction, what force is actually causing or acting in the radial direction to allow the vehicle to move in the circular path? So let's look at the forces. Let's look at our forces acting in the system. So on our vehicle, we're going to have a force of gravity down like this. We're going to have a force normal coming up like this. And rather talking about the angle of inclination, remember this is not an inclined plane, even though it looks like an inclined plane, we're going to talk about the banking angle. So this is called the banking angle. Alright, so let me pull up a different color here so I can draw in some different angles. So I'm going to extend this out. Remember, this is sort of the center of the circle here. And we have to remember, in between the incline and here, this is 90 degrees, because remember, It's called force normal because it's normal to the surface. So it's normal to that horizontal. I'm also then going to extend my y-axis, so this is my positive y here. Alright, so follow along. So because this here is 180 degrees, and this here and here is 90 degrees, this angle in here, I'm going to call it alpha. Beta plus alpha plus 90 degrees equals 180 degrees. So that means that beta plus alpha has to equal 90 degrees. This here and here has to be 90 degrees because this is the negative x-axis, this is the positive x-axis, which makes this angle in here alpha and this angle in here beta, because alpha plus beta has to be 90. So if I remove a lot of the messiness, because my goal here actually is to break the force normal into components, if I just then draw my axes here, I have force normal acting up here in the first quadrant, and I've said the angle between the x-axis, or not the x-axis, the y-axis, and the force normal is beta from the diagram to the left. That means that when I draw in my components, so I have force normal in the y, and I have force normal in the radial direction. So we say force normal in the y is going to equal, see, we're dealing adjacent here, so we're going to say force normal, because that's the hypotenuse, and the y is adjacent, so we're going to use cosine of beta. Where force normal in the radial is opposite to beta, so we're going to use hypotenuse, which is the magnitude of the vector, times the sine of that banking angle. So it's very similar to the force of gravity in inclined planes, where the trig functions seem like they're reversed. So it's actually this force normal here acting in the radial direction that is causing the vehicle to continue in the circular motion and not to slide out of the curve. So this is why racetracks are banked, because if they were on a flat surface and they had those very bald tires, you'd end up with a lot of car accidents because the race cars would slide out of the curve and potentially into the stands. So that would be very dangerous. So you need to have those banked curves on a racetrack in order for the vehicles to continue their circular path.